Thank you. Good evening. I'm delighted to be here and honored to be here to deliver this guest Gresham lecture tonight. And as Valerie was saying, I'm fortunate to be a professional astronomer and cosmologist. And as a professional scientist whose academic and professional life is devoted to the study of the universe, some of the biggest mysteries about the cosmos that surrounds us, I think it's really part and parcel of what scientists, especially fundamental scientists such as myself, should be doing is to go out and talk to people like yourselves and hear what the public at large have to say about our discipline and why should we be studying these kind of subjects and spending a non-negligible amount of time, effort, and money doing so. And so tonight I'd like to present to you the case as to why studying astronomy and cosmology, the biggest mysteries of the universe, is not only interesting and fascinating. Hopefully you agree, otherwise you wouldn't be here tonight. But it's necessary for the benefit and the advancement of the entirety of society. But before we go into that, I want to take you back to 1831, to this experiment that Michael Faraday did for the first time successfully, August 29, 1831. I did have a pointer here. Did the pointer here disappear? Josh, if I could have a pointer for later, that'd be really useful. So you can see in this experiment a smaller coil at the top, which is powered by a battery that creates an electric field. And that electric field generates a magnetic field around the electric current generates a magnetic field around the coil labeled A. And what Michael Faraday did, as was a professor at the Royal Institution, he took the smaller coil and started moving it up and down inside the bigger coil, the one labeled B. The bigger coil was just a coil of copper wire with no electricity, nothing in it, just an inert coil of wire. And what he noticed in the instrument to the far left is that all of a sudden an electric current was being induced into the bigger coil by the presence of a magnetic field that was varying in space as he moved up and down the smaller of the two coils. And that was a momentous discovery, what we now call Faraday's law of induction, which allowed Faraday to conclude that actually electricity and magnetism are not separate phenomena. They are linked together, and in fact, by moving around a magnetic field, you can generate an electric current, and vice versa. If you pulsate an electric current, you can exert a force onto another piece of wire, which is effectively the principle that's at the heart of essentially the entirety of modern technology, anything that's got to do with electricity, electrical motors, and so on, electricity generation, is based on this experiment that was done 180 years ago almost. Later on, James Clerk Maxwell came around, and he was able to encapsulate this principle in a neat equation up there. We don't really need to go into what this equation means, but on the left-hand side, you can see that there is an E for electric field. On the right-hand side, there is a B for the magnetic field. And so the two are linked. There is an equality sign in between, which means that electricity and magnetism are linked, and the two together now can work to our advantage in new ways. And so, for example, hydroelectric production is based on this equation. Electrical motors are based on this equation. The entirety of our electricity distribution network effectively follows from this equation, and that means that from that small experiment that was being done by Faraday so many years ago, out of curiosity, out of a wish to understand the fundamental workings of nature, well, this is what happened. You know, this electricity is everywhere. And it's really a curiosity that changed the way we understand the world today and the way we interact with our world today. But Faraday was not only a great experimentalist, a great physicist, self-taught for the most part. He had very little formal education, remarkably. He wasn't very good at maths. In fact, it was Maxwell who came along and then formalized in a neat set of equations what Faraday had discovered. But he was very good at explaining things to the public, and he was the first one to give what is still to this date known as the Christmas lecture series at the Royal Institution. You can see him here giving one of his 19 Christmas lectures, which of course were a great hit with the public because everybody could then go and hear about these new discoveries, these exciting new discoveries. And today, in fact, those discoveries are remembered not only by those who know about them, but in fact, if you look a little closely in your pockets, you can find a memento of what Faraday did, not on this side of the 20 pounds note, not obviously recognized this is not Faraday. The flip side, though, here is Faraday looking out of the 20 pounds note and delivering one of his Christmas lectures in the far right. And the interesting story is that when around 1850, at the time when Faraday was very well established and very well recognized physicist of his time, having made these incredible discoveries, among others, discoveries that would enable later for us to use levitation, magnetic levitation, for example, and other discoveries in chemistry as well. Well, the then Chancellor of the Exchequer was visiting his lab in the Royal Institution and was looking at the kind of experiments that Faraday was doing with this kind of curiosity that was at the time electricity. And the Chancellor asked, Professor Faraday, what is electricity good for? Why should we be concerned with this interesting, but after all, sterile curiosity that you're working with? And reportedly, Faraday said, one day, sir, you may tax it. And indeed, we do pay tax on electricity today, and if you happen to settle your tax bill with a 20 pounds note today, look at the face of Faraday that reminds you that, out of fundamental research eventually comes tax. After this point in time, as we know, the progress was immense and very, very quick. 1876, the invention of the telephone. 1880, Edison patenting the light bulb that we know today. 1888, far right, is the but the discovery by Hertz that you could transmit information wirelessly by using the same kind of electromagnetic phenomena that Faraday had been investigating. And in 1904, at the bottom, an invention that at the time didn't really take off. Maybe the name wasn't catchy enough. A German inventor called Christian Hülsmeyer patented a device called the telemobiloscope. Well, yeah, it didn't really catch, but it was, a few years later, when the Second World War came about, it was very useful when it became the radar, again, based on technology that had been developed out of all these fundamental experiments that Faraday was making. And so it's clear, history really teaches us that out of curiosity for the workings of nature, unexpected, world-changing technology and developments can follow and do follow. This was at the end of the 19th century, and at the time, physics made great strides forwards to the point that big figures, such as Lord Kelvin, around the turning of the century, said, there is nothing new to be discovered in physics now. Everything is done. All that remains is more and more precise measurement. And how wrong he was. As we well know, physics was all but done. In fact, the golden age of physics still had to begin. And again, as we shall see, it was curiosity-driven physics. And interestingly, the heavens, the study of the cosmos and the universe, had a big part to play in developing our understanding of nature with many deep, unexpected consequences. Here is a phenomenon that was driving physicists crazy at the time, and one that people didn't understand, Lord Kelvin notwithstanding. The fact that people understood that electricity and electromagnetic phenomena, radio waves and light as well, were some sort of wave, electromagnetic waves, we call them today. But for a wave to exist and propagate, obviously, people thought we need some sort of medium. The kind of sound waves I'm using to talk to you here tonight are propagating through the air in this room, and so it's the air that's being compressed by my voice as I speak, and that's why in space you can scream as much as you want, nobody hears you scream, because there's no medium through which waves can propagate. And equally, people thought, scientists thought, physicists imagined that there must be some substance filling outer space that was the medium through which light, electromagnetic waves, could propagate. And this postulated substance was called the luminiferous ether, the substance that would carry light. But here's the thing. Because our sun is not still in the universe, it's moving actually with a velocity of about 220 kilometers per second through space. And therefore, if we postulate the existence of this medium through which everything, including our solar system, is traveling, it follows that if the sun is traveling upwards, then there must be an ether wind coming downwards due to the relative motion of the sun to the ether. And the Earth is orbiting around the sun, and therefore it follows that, say, in the spring and in the fall, the relative velocity of the Earth with respect to the ether is changing because, in the fall we're going in one direction, in the spring we're coming around the other direction, and so in one of the two cases we're going more against the wind. In the other case we're going a little bit in the same direction as the wind. And as everybody knows, when we experiment this kind of phenomena with ordinary wind and ordinary phenomena on Earth, if you're going against the wind, you feel more pressure, and vice versa if you go with the wind. And it should follow, therefore, that the velocity of light should change depending on the season. Because if we are traveling the same direction as the medium that's carrying the light, the velocity should go down, and vice versa, it should be higher if you're going against it. Rather like when you are, say, going down with the river on a boat down the river or coming upstream. But the famous experiment in 1886 by Michelson and Morley demonstrated that that was not the case. The velocity of light was constant through the seasons. There was no way it could change within the experimental error of the apparatus. And so the ether theory was in trouble. It was in big trouble until this gentleman came along. And he actually found out that this little nagging thing about nature that hadn't been quite understood was actually very deep. It had very deep roots in the fundamental nature of reality. And in fact, the constancy of the speed of light was what motivated Einstein to formulate a special theory of relativity, which then formed the building block of the general theory of relativity in 1916. We celebrated the centennial, 1915, we celebrated the centennial of that just last year. And so, in order to understand what the special theory of relativity says, I thought I'd present it to you in a rather different way. So, despite what Valerie said, I being of Italian origin, I have no qualms in self-advertising in my book. A little bit, I do, but I pretend not to. And so I thought I'd try to explain to you special relativity using the most common 1,000 words in English, like my book tries to do. And just to give you a little bit of a context, why would I try and do a crazy thing like this, is because effectively I think that all of the kind of ideas that I'm talking about tonight, and some of them I will just sketch out very briefly, but all these kind of fundamental mysteries about the way the universe works are too important for them to be left to professional scientists alone, and we need to be able to communicate them effectively to people such as yourselves, who are interested, obviously, but don't necessarily want to get lost in too much jargon. Hence, the idea of using only the most common 1,000 words in English. You can see a word cloud over there of the words that are in the book to explain everything there is, starting from the universe, which of course is not one of the most common 1,000 words. And so I was rather taken aback when I discovered that I wanted to write a book about a subject without being able to use words like telescope, universe, gravity, particle, Earth, scientist, galaxy, moon, energy, cosmos, planet, Big Bang. None of those words are, unfortunately, in the most common 1,000 words in English. Would you believe it? And so what do you do, right? So, well, Big Bang I thought was easy, right? Big Bang I thought, well, I don't have bang, but I have flash. And so because it's a very hot and dense moment at the beginning of the universe, I'm going to call it the hot flash. But then my editor told me, no, you can't call it the hot flash, really. And I realized it wasn't a good choice. And so I'm now calling it the big flash instead. So the universe was easy. The universe was the all there is. Telescope is a big seer. Planets are crazy stars because they don't go around with the other stars, but they go back and forth on the sky, apparently. Earth is the home world. Particles become drop. Scientists are student people because we never stop studying stuff. Galaxies are star crowds, and the moon is the sun's sister. But the point was that I was trying to communicate these ideas in a simple way. So let's see how it works and whether it works for you in terms of the special relativity explained in less than 1,000 words. Dr. Einstein was to become one of the most important student people ever. He had a quick brain, and he had been thinking carefully about the building blocks of the all there is. To his surprise, he found that light was the key to understanding how far away things in the sky, crazy stars, our star crowd, and perhaps even white shadows, appear to us. He began by asking what he would see if he could fly as fast as light and someone else was coming toward him. He knew that the answer was strange. It didn't matter whether the other person was still or moving as fast as light. Mr. Einstein would always see the other person approach as fast as light. This is not what you would see if you drove a car towards another car. How fast the other car comes at you changes if the other car is moving or not. Mr. Einstein knew that things were different for light. Two student people called Dr. Michelson and Dr. Morley had tried a few years before to time light as it flew towards two mirrors, one of which was moving while the other was still. They found that it didn't matter which mirror the light was flying to. The time it took to get there and back was always the same. You could not explain this using the normal idea of space and time. Mr. Einstein then said that space and time had to be married and form a new thing that he called space-time. Thanks to space-time, he found that time slows down if you fly almost as fast as light, and that your arm appears shorter in the direction you're going. And so by looking at phenomena such as the ether wind that wasn't, physicists, and Einstein was the first among them, were able to essentially capture a new notion of what space-time is, and a notion that changes our perspective on the world. Time and space are no longer fixed and immutable, rather time becomes a malleable entity, and it depends on the state of motion of the observer, just like space. And there were other puzzles that people couldn't understand that seemed very academic. For example, here, this graph shows the intensity of light as a function of its wavelength emitted by a body at various temperatures, 5,000 Kelvin, 4,000 Kelvin, 3,000 Kelvin, the different colored curves. And so those are measurements that people could make in the lab, but the black curve through the top shows that whatever physicists could predict in terms of how that light should be distributed, how that heat should be distributed for these bodies, was completely off. It was kind of all right at the bottom right, but for a wide range of wavelength, it was completely incorrect with respect to what had been measured. And that, again, was a nagging issue in terms of our understanding of the fundamental blocks of nature, which was only resolved when Planck declared that actually the fundamental building blocks of nature were not continuous. They were in reality, discrete. And that was the cornerstone idea of quantum mechanics, the theory that to this date describes with uncanny accuracy the behavior of the quantum world, the microscopic world. The idea being that energy couldn't be a continuous quantity, but rather came in discrete packets that we call quanta. And again, this revolution that is at the basis of everything we have in our pockets, think semiconductors, for example, that make up our electronic devices, they wouldn't be even conceivable without the use of quantum mechanics. All of that came out of fundamental physics and fundamental research. But I now want to turn our attention to the sky, because that's perhaps the most unsuspected place from which great stride forwards in terms of societal benefits can come and do come from. Here's a picture of the great Andromeda Nebula taken in 1899. At this point in time, astronomers weren't sure at all what this nebula was like. This is a galaxy, the nearest galaxy to us, 2.4 million light years away. You can actually see it with your naked eye if you know where to look, and it appears rather more clearly if you look with a small binocular. But the point is that around the turning of the century, again, this turning point in the history of physics and humankind, scientists didn't know how to estimate the distance, and so it wasn't clear whether this was just some cloud of gas that was small and nearby inside our own galaxy, or whether it was an entire galaxy of its own with billions of stars further away and therefore much bigger, despite the fact that it appears so small on the sky. The controversy was settled by Edwin Hubble in 1922, 1924, he was able to measure the distance to Andromeda and determined conclusively that it was too far away for it to be inside our galaxy. And so all of a sudden, the size of the universe expanded because Hubble discovered the fact that those distant nebulae could not be local. They had to be far away, hence had to be very, very big. In 1927, he then went on to make another astonishing discovery. He then measured the velocity at which these distant nebulae were moving away from us, and that's the vertical axis in this graph, against the distance that he estimated them to be at, which is the horizontal axis in the graph. And he found an interesting thing. He found that the more distant objects on the right-hand side of the graph are also the ones that are moving away from us the fastest. And he did the bold thing of drawing a straight line through this set of points, a line whose slope is to this date called Hubbles Constant, a line that shows that not only these galaxies are moving away from us, but also it implies that the universe itself is expanding, because you can only explain the fact that all galaxies are moving away from us if we imagine them to be scattered on top of an expanding universe. And we would be moving away from every other galaxy as well, as the fabric of space-time itself grows with time, something that Einstein personally thanked Hubble for discovering in 1931 when Einstein visited Mount Wilson Observatory. And so this discovery changed completely our outlook on the universe, and the implications of this discovery have been ringing throughout cosmology to this date until last month. I'm just picking here one of the most fantastic examples of what this discovery has enabled us to do, which is, I hope you're all aware, the amazing game-changing discovery of gravitational waves only last month, February 11th, 2016. When scientists in the US announced the discovery for the first time of ripples in space-time itself, ripples in the fabric of space-time itself that had been predicted by Einstein's theory of general relativity for 100 years, but had never been discovered before. And this was done by using this instrument here. So this instrument here is a 4 kilometer, it's got two 4 kilometers long arms. Each arm, there's a beam of light, a laser beam of light, that goes back and forth, a mirror here and a mirror there, and the same in this direction. And so this instrument is being used to split light in this direction and in that direction, and as it comes back, it gets to be recombined here at the source, and it's used to measure the distance between this point and the end of each arm. It's about 4 kilometers. The point is that if you can measure this distance accurately enough, you can see this distance wobble as a gravitational wave passes through the instrument, a change in the fabric of space-time itself. And by how much does it wobble? Well, over 4 kilometers, about 1/millionth of the size of an atom. 1/millionth of the size of an atom. And this is, it's tiny, right? It's inconceivable almost that we can develop technology able to see that. But we've done it, and this is what the signal looks like. Those are the data obtained by 2 such telescopes. The data have been sonified, so the passing gravitational waves is a sound-like disturbance of sorts through space-time, can be converted into sound that we can hear, which is what you will hear in a second. And so you can actually perceive this new way of not looking at the universe, but actually listening in to the universe. Did you hear the chirping noise made? Not the sort of the background, but the chirp at the end where it goes whoop, and that's the signal that the gravitational waves has passed by. Let's. Yeah, that's the gravitational wave passing by, and what that tells us is that about 1.6 billion light years away, this phenomenon has happened. 2 black holes orbiting each other, losing energy and in form of gravitational waves, and therefore the orbit becomes smaller and smaller until they're too close together and they merge. And as they merge, a bigger black hole is formed, a black hole that's not the sum of the masses of the 2 black holes, it's slightly smaller than the 2 combined. And the difference in mass, about 3 times the mass of the sun, that's about 6 times 10 to the 30 kilogram, has been emitted in the form of gravitational waves. And that is the signal that we've picked up. So you might think that's all very well, but and it's astonishing and it's incredible, and it opens up an incredible new way of looking at the universe and listening in to this kind of cosmic science, understanding the nature of black holes, the distance to distant phenomena in the universe, and therefore dark energy, and so on and so forth. But why is it interesting for us? What did Einstein ever do for me? Well, next time that you pick up your mobile phone and you look at your map on the mobile phone, which is powered by a GPS signal, I hope you remember this man, because the kind of signals, the GPS signals that we get from geostationary satellites orbiting 36,000 kilometers above the Earth are used to triangulate our position here, and that is what gives you your position on the map. The thing is that without Einstein theory of special and general relativity, we wouldn't be able to use GPS at all, because the satellites are moving at a certain speed in orbit, and this implies that the time on board the satellite is changed with respect to the time here on Earth. And also they find themselves in a gravitational field, which also slows time down in a different way through a phenomenon which is predicted by general relativity. And because the triangulation relies on the fact that the clocks on board the satellites are exactly synchronized with clocks on the ground, unless we were able to accurately predict and correct for this general and special relativistic phenomena, within a day, the accuracy of our GPS positioning would be off by kilometers. I'm not talking centimeters, I'm talking kilometers a day. So Einstein is in there every single time you bring up Google Maps. So remember that next time you're looking for directions. So as I was saying before, the unexpected is where interesting phenomena lie, and serendipity, random discoveries that are game changers plays a big role in astronomy, in cosmology, and also for society. Here's a picture of the sky with the moon to scale. So I want you to focus not on the moon. I put it there just to give you a sense of scale, but I want you to focus on the small square here, which encircles a part of the sky that's fully unremarkable. It looks almost empty. It's a very small part of the sky. In fact, it's so small that it would fit inside the eye of a needle held at arm's length. So you can imagine it's really, really tiny. And yet, if we look into this eye of the needle with the most powerful set of glasses that we have currently, the Hubble Space Telescope, this is what we see. 5,500 galaxies inside that eye of a needle. And each one of those dots is an entire galaxy, which itself is made of hundreds of billions of stars. And all of those galaxies fit inside that eye of a needle. So you do the maths. If you multiply it by the area of the sphere, there are about 50 billion galaxies in the visible universe alone, and each one of them has hundreds of billions of stars, which is remarkable per se, but just the beginning of the story, because in fact, I hate to be the one that's breaking the news to you if you haven't heard this already, but 96% of the universe is missing, is dark. It doesn't show up in that picture. Everything we saw in that astonishing picture is only 4% of the total. And so we have discovered in the last 2 decades or so that the universe, of which we have maps such as this from the very early stage of its life, the relic radiation from the Big Bang, the universe is a lot more mysterious than we ever thought it possible. It's got a dark side that we need to understand. And so rather like Lord Kelvin said at the end of the last century, or the previous century, well, we're almost done here. All we need to do is do more and more precise measurements. The thing is that we could be finding ourselves in a similarly unstable position. A revolution in our understanding of the makeup of the world, of the universe, could be lurking around the corner, because in fact, our current understanding is far from being satisfactory. Let's be honest about it. Here is what the universe is made of according to the standard law. Well, everything you saw in the Hubble Space Telescope picture is this yellow little sliver here, not very much at all. There's another bit here in the pie that's gas and neutrinos and other stuff that we know about, stuff that is made of the same kind of particles you and I are made of, and that's fine. But the fact is that we think that 23% of the universe is made of dark matter and 73% is made of dark energy, both of which remain unknown and undiscovered. And so could that be the tip of the iceberg? Could that be that once we discover what this 96% is actually made of, our understanding of physics, and therefore eventually of technology, is revolutionized? Quite possible. We don't know what dark matter is made of, but we can put it in a supercomputer and simulate what the universe will look like if we could see dark matter. Here's a movie that shows what the dark matter should do, we expect it to do in the universe. It's been color-coded so that the dark matter is actually visible to you. So where you see high-intensity regions, bright regions, that's where most dark matter resides. And you can see that as cosmic time goes by, dark matter clusters and becomes more and more, it accretes around points of high gravitational pull, and gravity does its thing of creating filaments and structures. So the cosmic scaffolding of what the visible universe is made of. So we can simulate dark matter, we can tell that it should be out there because it influences all the other things that we see in the sky, but we can't, as of yet, measure it. We can't prove its particle nature yet, although this might change in the next 5 to 10 years. Other revolutionary discoveries in cosmology, the discovery in 1964 of the existence of a relic radiation, of a luminous echo of the Big Bang itself, which essentially heralded the era of our understanding of the universe as coming from a hot, dense Big Bang that gave birth to everything there is, made the headlines in 1965. That's the New York Times back then. Nowadays, we have much better maps of the sky in microwaves. You can see here the picture of the visible universe as it was 380,000 years after the Big Bang. That's about 13.8 billion years ago. And you can see slightly hotter regions in red, slightly cooler regions in blue. Those are regions that are the seeds for the formation of the galaxies that we see nowadays in the sky. And if we translate this map into a statistical language, a language that we can plot using graphs and quantitative measurements, then we see that our theory, our cosmological theory that contains Einstein theory of general relativity, dark matter, dark energy in red, is a beautiful fit to all this high precision data in blue that have been gathered by the Planck satellite in 2015. So clearly there is something here. We have a beautiful theory that fits everything we can see in the sky and beyond in terms of dark matter, dark energy, and yet it doesn't make any sense. Could we be on the verge of a revolution in cosmology, a revolution that, once properly understood, will change the face of society in ways that we cannot begin to imagine? Having said that, I want now to conclude by giving you 4 reasons as to why societies not only need, but cannot do without cosmology, astronomy. The first one is inspiration. Inspiration not just for the general public, but specifically inspiration for children and young adults for STEM, science, technology, engineering, medicine subjects. 80% of physics students cite astronomy and cosmology, particle physics, as some of the reasons why they went to studying physics at undergraduate level at university. And that's greatly encouraging because it's telling us that these big questions are really a magnet for young people of all sorts of backgrounds and all sorts of provenance to study physics, to studying, if not physics, engineering, space sciences, all of these STEM subjects that then are effectively fueling growth and economic growth for the entirety of society. Only a tiny, tiny fraction of our students, even PhD students who specialize in astronomy and cosmology, end up as professional academics. Maybe only about 10% of our PhD end up with a permanent position in a university. But that doesn't mean that their training is wasted. The training in astronomy and cosmology is wasted because what we teach them are great transferable skills, data analysis skills, mathematical modeling, analytical skills, all skills that are in great demand throughout society, not just here in the city of London, but further afield. And so our graduates then go on and contribute those vital skills to the wider economy and do so at a very, very high level indeed. Here in particular, I want to flag the fact that we need to attract and retain more women to science and physics in particular. Physics is a little bit in a dire spot in terms of not attracting women. We're doing pretty well. We almost have not 50% equality at undergraduate level, but close at Imperial, for example, where I'm from. But then this ratio drops constantly as in terms when people progress to the rank, and we have only about 15% female professors, and that's something that we need urgently to address to redress this imbalance and really put out the message that physics and astronomy and cosmology is for everybody. It's not just for the boys. And I was looking at here in the room before the lecture started, and I was delighted to see a good fraction of women and young women as well in the room, certainly well above the 15% that we master at Imperial. So that's really, really good and encouraging. The other point to emphasize about how astronomy and cosmology are done today is this. People, when they think about astronomy, sometimes there's still this notion of this romantic notion of the lone astronomer going out with a telescope and making these groundbreaking discoveries, which was a picture that until 30, 40 years ago was pretty much true. Here I've got two examples. Again, I've on purpose selected two great women astronomers just to, again, break the idea that it's only white men with a beard and a white coat making discoveries. So Vera Rubin in the 70s was one of the strong proponents of the idea of dark matter in galaxies, for example, and Jocelyn Bell Burnell in 1968 discovered pulsars at Jodrell Bank. And they did it on their own, essentially, almost unaided. So very much the idea of going out with a telescope. Here, this is the spectrograph in this case. In this case, it's a radio telescope and looking at the universe. Today, cosmology and astronomy are very different. Those are big science collaboration. That's a Fermi-LAT collaboration, a gamma-ray satellite. That's part of the LSST, Large Synaptic Survey Telescope team. Nowadays, cosmology and astronomy require big instruments, and this means big teams. So we're talking hundreds, thousands of scientists, engineers, data scientists working together, simply because the problems have become so much harder. It becomes a planetary effort to advance astronomy. That means that the money involved also becomes of planetary scale. And so the obvious question is, what is the bang for my bucks? What do I get as a society? Why should we be spending money, especially in times of belt tightening? As we know, tomorrow will tell what the next round of cuts is going to be. What do we get for these large-ish sums that we spend on astronomy? Well, the thing is that while these big telescopes are expensive, a ground-based telescope will set you back of order $100 million, let's say, and a space-based mission like Planck will be $1 billion tag. So this is the kind of big money we are talking about. But then, if you put it in context, big astronomy means big discovery that are actually relatively cheap. For the price of a coffee per European citizen a year, you can fund a big project like one of those big observatories for a decade or two, a project that will produce thousands of research papers, will inspire hundreds of thousands of kids for astronomy, and bring about major breakthroughs in our understanding of the universe. All of that for a price of a coffee. So next time you pick up your latte in the morning, maybe one day you can give up your latte and say, well, actually, I'm going to save for astronomy instead. In the grand scheme of things, really, this is not a lot of money. Here is government spending broken down by subject. In 2010, that was at the sort of the height of astronomy spending before the tide changed. So here's global UK spending in 2010-11, about 700 billion pounds government spending. So in order to find astronomy, where do we need to go? Well, we need to look at BEAS, business, innovation, and skills, which is this little bit here. That's 24 billion pounds. And within BEAS, we need to look at science, which is about 6 billion pounds. And within science, we need to look at the research councils, which is 3 billion pounds. And within the research council, we need to look for astronomy, which is less than 400 million pounds. Okay, so that's 0.05% of the big spending. It's not a big amount of money in the grand scheme of things. You could with this amount of money, you could run the NHS for the whole of one day, or you could buy 4 F-32 advanced fighter jets. So it's not a big price to pay, to understand the fundamental nature of the cosmos. And the UK as a nation is doing pretty well. UK astronomy is world leading. Here is a graph showing comparison of the UK with all the major other players, US, Germany, France, and Italy, in 5 years, 2008 to 2013. the metric here doesn't really matter. It's some sort of citation metrics. How many times research done in those countries has been cited by peers. Therefore, it's a measure of impact. You can see there's two measures of impact. One is blue and one is red. It doesn't matter what they are. But whatever way you choose to measure, the UK comes out on top, even before, in terms of, once you normalize it by the number of researchers and spending and so on, even above the US. So really, this country is doing really, really well, despite chronic underfunding, one could say, of science. Here is the average spending for science in the UK over time from 1996 to 2012 as compared to the G8 average here and the USA up here. You can see this is really, really lagging behind. It's now dipping below 0.5%, and despite this relatively shortage of funds, we just saw how UK astronomy certainly is coming out tops. It's a great outcome for UK science. And finally, that's the economic case. But I talked about revolutionary new ideas coming out of astronomy, and here are just a few examples that I selected for you. You wouldn't dream of using techniques that have been developed for astronomical data analysis and image analysis to improve tumor diagnosis. But this is what is being done by various research groups that are trying to use techniques that we have developed, or they have developed, to clean up and sharpen images of the cosmos of the kind that we just saw, to provide a better view, a non-invasive view, for example, of breast cancer that can be diagnosed earlier and therefore save lives. The computer codes and very sophisticated simulations of the kind that we saw with the dark matter example have plenty of applications in society. For example, in transport, these kind of codes have been used to improve the simulation of aerodynamics, in this case for Airbus, to improve the design of planes, reduce fuel consumption, and therefore fight climate change. And again here, another example of a scanner, in this case MRI scanner. MRI and PET scanners are the direct offspring of research in particle physics. And so every time you go, hopefully not often, I hope not, but if you should ever go for an MRI or PET scanner, remember, this is particle physics. This was particle physics research 20 years ago, now in every hospital around us. So I've given you 3 reasons why astronomy is important, why astronomy is unexpected, why astronomy and cosmology are fundamental for society. But I've saved, of course, the most important, the strongest reason in my eyes for last. And the reason is that cosmos is culture. In other words, this divide between arts, humanities, and science doesn't need to be so. And in particular, I believe strongly in the fact that we should be doing research of the fundamental kind, be it in astronomy, be it in particle physics, be it in any other area of research, for the sake of advancing knowledge itself. In other words, it would be a mistake to focus our sights on the next technological breakthrough 5 years down the line. If Faraday had done that in 1830, we wouldn't be here tonight talking in this lecture theater with the kind of technology we have. We need to pursue curiosity-driven research because of the unexpected, because of the kind of long-term views that will almost inevitably emerge when we pursue knowledge for knowledge's sake. I want to end with a great example of that. In 1969, when Robert Wilson, the first director of Fermilab, the particle physics accelerator near Chicago, was asked by Congress how to justify the huge amount of spending that was being allocated to the laboratory. $250 million at the time, about $1.6 billion in today's money. And so Congress people wanted to hear reasons how, at the height of the Cold War, this investment would help the US fight off the Soviets, of course. But Robert Wilson wasn't having any of that. And so Senator Pastor asked Wilson, here we are asking for $250 million to build a machine that is an experimental machine in fundamental high energy physics. And we cannot be told exactly what we're trying to find out through that machine. But Wilson said, this new knowledge has nothing to do directly with defending our country, except to make it worth defending. And I think that's the fundamental reason why we should be doing this, because it's one of the biggest quests in humanity, the search for knowledge, the search for the ultimate fundamental reality of the cosmos. On that, going back to the book which tries to explain this fundamental reality using the most common 1,000 words, it's out there. If you want to grab a copy, it's a beautiful little book. It's only £10, really cheap, and makes for a fantastic Christmas gift. I know it's a little early for Christmas, but even so. If you don't want to buy the book and you don't want to read such a long book, about 76 pages, what I've done here tonight for you is try to summarize everything that's in the book using only the 10 haikus that open each one of the 10 chapters of the book. And so I've tried to paint a picture here of everything that we know and that we hope to be able to understand about the deep mysteries of the universe using only 63 different words. Here we go. In the clear night, her dark hair mirrors the stars. Blue words going around points of light. Behind the stars, space-time grows silent. Hot kisses leave light very tired. Her pink lips stay dry in the heavy dark rain. A soft song might tell you dark stories. With the last breath, a blushing of light from faraway stars. A silent end, times of light, half remembered. So many words, all that can be is. Everything opens at the smallest touch of a rose. And I would like to leave you with that, and we'll leave you with a thought that in this very room, right now, right here, if you put your hand out, or even if you don't, about 15 million dark matter particles are streaming through your hand per second, unbeknown to us. Hopefully, this will change in 5 to 10 years' time. We hope to be able to build detectors that will actually discover those particles. And so, as I know that the Chancellor is looking for new ways of evening out the budget, I hope nobody goes and tells him that there are so many dark matter particles around here, because otherwise he might think, well, actually, one day I might want to tax it. Thank you very much. Thank you.